Just before I continue with the last example, I had an email from one of the students creating example 4.2, and I thought I'd just explain it or just provide a further clarification on that. I haven't replied to the email, so I'll just explain it in this lecture. And I thought it would be of interest to other students. And the query was in this example 4.2, why are we multiplying by that 0.3? Let me just get my pen out. In this particular one, why do we keep multiplying by that 0.3? Why are we not just using the values directly from that table? So, for example, the 27 that you see, that 27, that point over there, why are we not just multiplying by that? And it comes back to this table, and table 4.1. You'll see there, for example, the medium radius pen, that value of 27 was this. So why didn't we just use that 27? We're talking about the equivalent length of the pipe. Now what you need to just take a note of, note in this table, the unit actually of measurement is the diameter of the pipe. So it says the equivalent length. So when it says 27, it doesn't mean 27 meters. That's the equivalent length of that fitting. It means 27 times the diameter of the pipe. So, for example, a medium radius bend for you'll get medium radius bends for example, a 50 diameter pipe, a 100 diameter pipe, a 200 diameter pipe, a 400 diameter pipe, like that. Right. So, and each one is different. The actual equivalent length will be different. It can't be 27 meters for all of those different diameter pipes. So that's what this is a function of the diameter of the pipe. So maybe to help you understand it, let me just erase this arrow, and just to what you maybe if you want to add here, you can say 27 times the pipe diameter. Right, so for each of these values, that's what it is. And if you look at the heading, they note that it says the diameters of pipe. So it's 27 of the pipe, 27 pipe diameters. That's what it's simply telling you. That's the equivalent length for that medium radius bend, 27 pipe diameters. So for the gate valve, for example, at that point you have that value of 17. It means that the equivalent length, the amount of friction produced in that gate valve is 17 times the diameter of that pipeline that you're fitting that gate valve to. Right. So if you're fitting that gate valve to a 100 diameter pipe, it'll be 17 times 0.1 meter. Right. That's the 100 millimeter is 0.1 meter. So if you're fitting that gate valve to a 100 diameter pipe, it'll be 17 times 0.1 meter. If you're fitting that gate valve to a 1 meter diameter pipe, then it'll be 17 times 1 meter, like that. So that's how you read this table, and that's how this example 4.2 was worked out. And we stopped at example 3 for 4.3 yesterday. This is again in example 4.3. I went it very quickly, and you can go through it yourself. It's just showing you the application of that equation that we've used, equation 4.3. Let's go back here, and that's this equation 4.3. It is showing you how to apply this equation by substituting numbers. It's illustrating this equation to you with the aid of actual numbers in it. And something you could easily follow yourself. The next example that occurs in this that's in this in the set of notes that I've given to you, or in this chapter or section of notes that I've given to you. Example 4.4 again, a very simple example, but it's an illustration of the nomograph that's given to you earlier. This on the figure 4.6, you look there, if you see there, this is a nomograph, and this is for, it helps you to solve the Hazen-Williams equation. Instead of actually substituting into the formula, you could use this this nomograph. And the way it works is you have 4 unknowns. You have the discharge. If you look at the graph here, let me just enlarge it a bit so you'll be able to see it clearer on the screen. Let me just go here. And you can see there's 4 vertical lines, and each one has a separate heading. The first one is the discharge in liters per second. So that will be your Q, capital Q. that you're looking at over there. The next one is the diameter of the pipe in millimeters. So just take a note of that unit. The third one is the head loss, HL. So that's the HL that you get from the equation, the Hazen-Williams equation. And the last one is the velocity. Velocity and discharge are related to the continuity equation we spoke about yesterday, and the velocity also appears in the Hazen-Williams equation to work out the friction losses over there. So you've got these four unknowns, and if you know any two of them, you can then determine the remaining two using this nomograph. And the way it works is the two values that you know, you plot it on this wherever it appears on this. So you'll plot those two, and then you join them with a straight line, and where it crosses the other two axes, those are the values you would read off. So for example, let me just, give you an example. And let's say if I had the 300 millimeter diameter pipe, so I'll make a dot, the 300 millimeter diameter pipe, and the flow in that 300 diameter pipe, let's say for argument's sake, was 1 meter per second. So however I've determined this, I'm not going to go into that, but I have these two variables that are known to me. So I have 1 meter per second flow in a 300 diameter pipe, and I now want to know, well, okay, if that's what's happening in that pipe, in the 300 diameter pipe, it's under pressure, and I have a flow of 1 meter per second. What's the head loss in the pipe, and what's the discharge in the pipe? Those are the other two variables. So you take a ruler. Now, I don't, with the equipment I have, I can't actually draw a straight line on the screen, so I'm just going to use my mouse, and it's not going to be that straight, but you'll get the idea. So you take your ruler and you draw a straight line across like that. Through that, and where it crosses the two remaining axes. So in other words, I can, from this nomograph, I can then predict, well, the discharge in that pipe, the flow in that pipe is actually about around 75. It'll be around 75 liters per second. So that would be, I can, from this nomograph, and the head loss in that pipe would be around 6.5 meters per 1,000 meter length of pipe. Right? So for every 1,000 meters of pipe, I'll expect a head loss of around 6.5 meters per 1,000 meters of. So for every 1,000 meters of pipeline, I'll expect the head loss of 6.5 meters. So that's how you read off this nomograph, and that's what that example is simply illustrating to you. Now, there's one qualifier in this whole nomograph. If you look at the Hazen-Williams equation, let's just go back here to the Hazen-Williams formula. That was the Hazen-Williams formula. You'll recall in from yesterday's lecture, and you'll notice it has a C value. Right? The constant, the coefficient C, and that's dependent. If you look in table 4.2, the various C values were given to you. So it's dependent on the pipe material. Right? So that equation, this equation, Hazen-Williams equation, actually is a function of the pipe material. Now, in this nomograph, you don't see the pipe material appearing here, as you read it off here. So how do you compensate for that fact? You notice right at the bottom, in the heading of that graph, it says there that that nomograph is based on a C value of 100. Right, so that's what this is based on. It's based on a C value of 100. So that would mean it's meant for a cast iron pipe of about 20 years old or something like that. So that's what it's been derived for. That's what that nomograph is derived for. So what if you have a different value? So what if you have a value of 130, C equals to 130 or 120? Then in the notes in the next page, you're given a correction. Table 4.3 gives you the correction factors for different values of C. It tells you the correction factors to determine head losses from that. So if you want to determine the head loss in the pipe, and that's what you're normally interested in, so how would you correct that? This is what's in this table. You got you look here for C values, for different C values, what the K value, what the K correction factor is. And you can see the corrected, the formula is given to you in that line on the top. the corrected head loss is that this constant K that you would read off from, or the correction factor K you would read off from this table, and times the head loss that occurred at C. So this value, this head loss that occurred at C equals to 100, that's what you would pick up from the nomograph. So whatever value of head loss that you read off in this, so if we read off a value of 6.5 from this head loss, like what I illustrated now, and if you had a C value of, let's say, 140, then you would have to now come to this graph, and then you would see, look it up. It starts off at 80. You got to know how to read it. So it starts off at 80, goes to 110, and then it continues at this point from 110 to 120, 130, 140. So you got to read this graph, go like that, go across here, and come down again like that. So if we had a value, C value of 140, then whatever value for HL that we read off from that graph, I had read off a value of 6.5, so I'll multiply it by 0.54. So it means roughly around 3.2 or somewhere around the somewhere around the 3.3, somewhere around there. That would actually be the corrected head loss for a coefficient of 140, C equals to 140. So that's how you use this table to correct it for different C values that you would have. That's for the different coefficients, Hazen-Williams coefficients. Okay, so that's example 4.4. And I'll
Sir,
leave it. Yes, you can. Is there a query?
sir, on the loss of head on the graph, you said it was 6.5. Wouldn't you read the graph as 5.5?
Oh, oh dear. Maybe I made a mistake. Let me just
No,
go
I'm
back.
just to know how
Uh,
to read it.
Thanks for that. Yes, you're absolutely correct. Thanks for that. I was reading it in the wrong direction. Okay, yeah. This shows how careful you've got to be with this graph. Some of them are, if you read it, if you look at it carefully, some of the axes are increasing upwards and some are increasing downwards. So thank you very much for that correction. Yes, I made a mistake there. You are absolutely correct. It should have been 5.5, right? From that graph there. Thank you again for that. Uh, right, so those of you, the rest of the class, just make a note for that. That should have been 5.5 there. There's example for 4.4, and exactly what I've explained to you. You can, I'll leave it to you to go through this, and you'll apply. It's the same application of that over here. Right? So you got a 250 diameter pipe. So you got the diameter of the pipe, you got the flow that's required in the pipe, 60 liters per second, and this time you asked, you requested for the velocity of the flow and the head loss, and for C equals to 100. So if you have C equals to 100, you can use that nomograph, and then the second part is, well, what if C equals to 140? Right, so how do you do the corrections for that? And exactly as I've explained it to you, you'll see that correction being done in this particular example. This example is leading you through the process, so that's why it first asks you for work it out for C equals to 100, because that's what you're going to get from that graph, from the nomograph, and then correct it for C equals to 140. In practice, if you had just a graph with if you were working with this C equals to 140, then you would still need to do it for C equals to 100, because that's what the nomograph is, and then you would then do the correction for C equals to 140. Okay, so that's example 4.4 explained, and then example of 4.5, and again, this is an application of that equation 4.3, where you have head losses in it, in a pipeline. Just to the diagram on the page on the right hand side. Now, unfortunately, my screen, if I try and show it all in the screen, it'll get too big, but let's just see what we can do over here. Right, so simply put, what do you have here? You have a point B, in the, okay, you're looking at the graph, you see the ground line, that's the ground surface that you have, and the datum is set at the bottom left-hand corner. So at A, the elevation that you have there, whatever, that's set as 0. So we're not using, for example, mean sea level or whatever like that. So our datum point is at point A. We're using the ground level at point A as our datum for this particular problem over here. Right, so you have a point A. At point A, there's a pump station. So you that pumps the water up, and it's pumping it towards point B. Right? So it's supplying water from point A. You're supplying water to point B, and you're pumping the water to B. Now, the pump itself will pressurize the pipe so that the water can flow uphill. Right? Naturally, water would not just flow uphill, but gravity will make it go downwards. So that's the purpose of the pump. So you have some sort of a reservoir, a storage reservoir at point A, and we're then going to draw off water from the reservoir. That's what you see in the bottom sketch there. And we draw off the pump draws the water, so the pump inlet draws water from the reservoir, and then it pumps the water to point B. And the pressure that that pump creates at point A is 550 kPa. Right, so that's the pressure that that pump would create at that point at point A. Now, I told you in last week's lecture that we generally would work with meters of head, so we would then divide that 550 by 9.79, if I recall, and that would convert that to meters of head at point A. So that's the pressure that's in the pipe now at point A, pipeline at point A, and that's what that point has been plotted at that point over there. So that's the plotting of that, and you can see if you took 550 and you divided it by 9.79, you would then get 56.2 meters of head. Right. Instead of working with kPa, we generally prefer to work with meters of head, and our datum is also at 0 meters head over here. Right. So that's the first conversion that we'd have. So that's from point A, we're supplying water to point B, and point B is not at the datum level at 0. The ground level at point B is given to you as 9.1 meters. So if you look down there on the sketch where I've pointed to the arrow there, so 9.1 meters. That's the ground level at point B. So that's where we're supplying water to. And then you're told that the residual pressure at point B is 200 kPa. Now, what does that mean, residual pressure? It means that the pressure in the pipeline after all the head losses has occurred is 200 kPa. So when you're starting off at point A with a pressure of 550 kPa, and then the water flows from A to B. The length of that pipeline is 1,500 meters. The diameter of that pipeline is given to you as 300 millimeters. So the water is going to flow from A to B in that 300 millimeter diameter pipe. The length is 1,500 meters, and the head loss that occurs in that pipeline is such that by the time the water reaches point B, the pressure has now reduced to 200 kPa, the pressure in the pipeline, so the hydraulic pressure in that pipeline. You'll recall from that graph that we spoke about. Now, when we talk about the hydraulic head here, let me just go back to this, if you recall, figure 4.4, we're talking of the piezometer pressure in the pipeline. So we're not accounting for the velocity head in the pipeline. We're talking of the piezometer pressure in that pipeline at that point over there. So let's come back to our problem. Okay, so that's what this residual pressure means. It's if I were to then drill a hole in that pipe at that point, at point B, and put a piezometer tube in there, then that's the pressure reading. I would get 200 kPa. Or another way to look at it is if I took that 200 kPa and divided it by the 9.79, and I would convert it to meters of head, then I'd get a value of 29.5. Okay, 29.5 is relative to the datum of 0, but if I had to put up, if I want to convert that to a piezometer reading, it would be 29.5 minus the 9.1. Right? So because that's the elevation at that point A. So at point B, the elevation is 9.1. So the pressure in that pipeline at point B would be 29.5 minus the 9.1, which is the elevation head. So minus that height, that's the elevation head that I'm showing you with my cursor right now. Right, so that's what it's telling you, that you would get, that's what the residual pressure. So there's quite a bit of head loss in that pipeline from point A to point B. And what you want to determine in this particular problem is what will be the flow, or how much of flow would arrive from point A, how much of flow would you then get at point B from that coming up from the supply reservoir that you have there. And then you also have another supply, water supply to the same point B, so the same particular pipeline. There's an elevated storage tower at point C. The ground level at point C is given to you as 12.2 meters. So, for example, that's what it's telling you. So the ground level there is at 12.2 meters. So it will help you to actually draw this into the sketch. And then the tower itself is 30 meters above the ground level. Right? So 30 meters above the ground level, that's where the full supply level of water in that elevated storage tower is. So 30 plus that 12.2 would give you 42.2 meters. So that's how we arrived at this value here. Now you'll notice this is given in meters, and the elevation from the datum, the elevation head, that's also in meters. So there's no kPa being used here. Right? So that's how that was obtained over there. So you have this now the elevated water tower, and from this elevated water tower, there's a 250 millimeter pipeline, and it's 900 meters long. So the pipeline is 900 meters long, and it's 250 millimeter in diameter, and it's also supplying water to point B. And again, you'd have some friction losses, and by the time the water arrives at point B in that pipeline, again, the pressure in that pipeline, we're assuming, is 200 kPa. Right? It's the same pipe. It comes so that it can only have one pressure at point B because these two pipes join at that point. So they're going to intersect and they join there. So the pressure at point B, the piezometer pressure at point B is 200 kPa. And the question here is, how much of water would be flowing in that pipe? Right? So how much of water would be delivered in liters per second? So that's what we want to determine. So the total water that can be supplied to B would be equal to whatever the flow you have in the left-hand pipe plus the flow that's taking place in the right-hand side pipe, and that will give you the total flow at point B. So it's a long description of what the question is, but I've spent some time just to help you understand these values in terms of the equation also that we need to determine. Right, so example 4.5, it says an extremely simplified water supply system, and it's true, it is extremely simplified, consisting of a reservoir with lift pumps. Lift pumps, this means that it's going to increase the pressure, so you're lifting the water. Right? So simple as that. You're going to lift the water as though you're lifting the water to a certain height, increasing the pressure in that pipeline. Elevated storage, so that's the elevated storage at point C. Piping, we know about the pipe from A to B and from C to B. And load center, right? So the load center, that's where we're supplying the water. That's what, in simple terms, it means. That's the where you're supplying the water. So whether it's a house or whether it's very unlikely to be a house for such a large pipeline. Maybe an industry, a factory of some sort, or it might even be a suburb or whatever, or might even be another reservoir at that point that you're designing to fill water into. That's why they just use the word load center. So we're not describing what we're supplying the water to. So whatever it is, whether it's a township, whether it's another reservoir, whether it's a huge factory or whatever we're supplying water to. So that's the load point. And that's where the water is withdrawn from those pipelines. So that's what's shown in figure 4.7. And then comes the question, based on the following data, sketch the hydraulic gradient for the system. So now you're given some information. The first part of that, that's for at point A, and then the second part is for point B. And you notice that the elevation head at point A is 0, so that's our datum. We're taking A as the datum point, and the pressure in the pipeline at point A is 550 kPa, Then at point B, same thing again, the elevation head is 9.1 meters, so that's how high above ground level point B is, and the pressure at point B in the pipeline is 200 kPa. Right, so if you put a piezometer at the point B, that's what you get a pressure of 200 kPa. And if you put a piezometer at point A, you get a pressure of 550 kPa. And then similarly for point C, similarly you're given the data, the elevation head, uh, the pressure in the pipe, pressure at point C, and that's it. So that's you're given that information over there. So the first one is to sketch the hydraulic gradient for the system. To do that, to sketch the hydraulic gradient, let's go back and this go back to the previous figure 4.4, and you'll see we will continuously refer to this figure 4.4, so it's important for you to understand this diagram. The hydraulic gradient, that's the line that you're looking for. So that's what you want to plot. And you can see that to plot that line, you need the piezometer pressure. So whatever the pressure in the pipeline is at that point, at point A, and whatever the pressure in the pipeline is at point B, that's what you're going to draw those two lines vertically, and you join it, and then that gives you that line that's called the hydraulic grade line. Right? So we after that hydraulic grade line, and the slope of that line, that's what we refer to as the hydraulic gradient. Right? So we want the hydraulic grade line in this particular question. Uh, and so it says the hydraulic gradient, but if you're sketching it, then what they're saying, sketch the hydraulic gradient line. Right? So that's maybe more correctly if you know, put it that way. So to sketch that, like I told you, you need the piezometer pressures at point A and point B, and that's what you're looking at it. So the pressure at point A would be okay, let me just go back here to the diagram. Maybe I didn't explain it well. That pressure there, if you look at it, the hydraulic, it's the pressure relative to the datum. Just remember that. So that term there. So it's the sum of the, so in that equation, if we sum up those two terms at that point. So when we talk of hydraulic gradient line, those are the terms that we need to sum up to get those values. So that's what's being done in this example here, and you can see for point A, that's what's being done, and the 550, like I told you, divided by 9.79, and that's how we got that 56.2 meter, the head at point A. Right, so, or the pressure at point A, if you want to talk it, but we generally, when we're using meters, we'll say the head at point A. Similarly, for point B, at point B, you can see we then have the elevation head is 9.1, and then the piezometer pressure is 200 kPa. 200 to now you have to add apples with apples. Right? This is bear that in mind. So 9.1 is in meters, 200 is in the kPa. So that's why the 200 is divided by 9.79. So that you got meters and meters, and then you add it up, and then you see that you have 29.5. And then that's plotted in this graph, 29.5 relative to the datum line, and you just join those lines, and that gives you the hydraulic gradient line between A and B. And then for between C and B, similar process again. We then will at point C, you now have the elevation head. So let me just get my pen out again. At point C, so we already know we've done it for point B. If you're doing point B and C, if you're doing the line between point B and C, B was done when we did the line between A and B. So we know what's happening at point B. So we only need to do for point C now. For point C, you have the elevation head plus the elevation in the water tower, so or the piezometer pressure at point C. Right, your elevated tower is like a tube over there, and that's filling up to 30 meters over there. So you then have that 42.2 at point C, and you just draw that on the graph, and that's what's been drawn, 42.2. Join those lines, and then there you have it, the hydraulic grade lines between those two. So that's the first part A that's been answered over there. Then the second part of it now for these conditions, so that was the pump with a pressure of 550, and it means that the elevated storage tower, we're assuming it's full right to the top. You can see at that level, we're not working with the bottom water level of that elevated tower. We're working with the top water level, 30 meters. So for these conditions, compute the flow available at point B from both supply, pump, and elevated storage, and use a C value of 100, and the pipe sizes are as shown in the diagram. 250 millimeter in BC and 300 millimeter diameter in BA. So that's compute uh, so the flow available. So that's what we want, is the liters per second that would be supplied or that would be flowing in each of those pipelines. To do that, in this particular example, we're using the nomograph, and it's only up to this point that we will use the nomograph. This for some information for you. In next week's lecture, we will proceed to use the Hazel-Williams equation directly. Right. So I'll show you how we can solve the same problem just by using the equations themselves and come to the same answers also. So from next week onwards, we will not use the nomograph. We will actually use the equations, and it's simple because most of the time in practice you would want to set up a spreadsheet. And then with a spreadsheet, it's not so simple to use a nomograph. It's easier to just use the equation. So that's why we'll use the equations from next week on. But for now, for today, we're using the nomograph because it gives you an idea of what we're actually doing. Right. So we now want the flow in pipe AB. Right, so whatever is throughout that length of the pipeline, the diameter is not changing, and we're not adding any water in between. So for that entire length of the pipeline, the flow in terms of liters per second would be constant. And that's from your continuity equation. V is not changing, and A is not changing as the water flows between those 2 points. So Q would be a constant at that point. So to determine that, for the second part of it, we need to know what's the head loss between A and B. Right? What's the head loss between A and B? And that's simple. We have, for example, the hydraulic head at point A was 56.2, and we know that by the time it arrives at point B, the hydraulic head that's left in that pipeline is 29.5 meters. So the head loss would be the difference between those two values, 56.2 minus 29.5. So that would be the head loss in that pipeline, and that's what you see in this. So the head loss between A and B is 56.2 minus the 29.5, so 26.7 meters of head loss that's occurring in pipeline AB. That by the time the flow reaches point B from A to B. To convert that to a head loss per 1,000 meters, because we know our nomograph, if we go back to our nomograph, that's the only reason it's being done here. The head loss here, you can see, is meters per 1,000 meters. So to be able to plot that point on the nomograph, that's the reason it's been converted. So you see head loss per 1,000 meters. So you take the 26.7 and divide it by 1.5, and you'll get 17.8 meters per 1,000 meters. Right. So that's the head loss for every 1,000 meters. Excuse me a minute. Sorry for that. I just needed to clear my throat. The way it's written, I know some students sometimes battle to understand it. You might find it easier to just say 26.7 meters over 1,500 meters. Right? So you can work it out first per meter. So 26.7 divided by 1,500 meters. And then you want the head loss for 1,000 meters. So then whatever answer you get, you just multiply it by 1,000. Right? So that's how you end up with that 1.5 there. Then, so you now worked out that the head loss between A and B is 17.8 meters per 1,000 meters. And now you can go to your graph, and you know two values on that graph. You know what the head loss is on your nomograph, and you also know what the diameter of the pipe we're using. We do have a 300 millimeter diameter pipe. We don't know the Q, the flow in the pipe, and we don't know the velocity of flow in that pipe. And so we can now go to our graph, and we would plot those two values, the 17.8 and the 300 diameter pipe. Now, again, I don't have a ruler or something like that to be able to do it accurately. I'll just give you the gist of it, of how you do that. I've already explained it to you earlier. But let's see. So we're starting off with a 300 diameter pipe. So we make a dot at that point. And then the head loss in meters per 1,000 meter, we said around 17.8, so almost around 18, somewhere around there like that. And you would then now take your ruler and you want to try and join that. Now I'm using a mouse, so just bear with me. I'm not going to come to the exact answers, but roughly you get the gist of how it's done. And this means that you can then read off Q from that from that axis, and you can then read off the velocity from that axis. It doesn't actually, the question doesn't ask you for the velocity. They're just asking you for the Q value. And if you go there, that's it's been done for you. You can do it yourself. You get the answer of 133 liters per second. Right now, I'm using a mouse, so I couldn't get that quite accurately. I went to about somewhere 140, 145 or something, but it's 133 if it's plotted properly, if you properly use a ruler and plot it from there. So that's where that answer came. So in pipeline AB, uh, the flow in that is 133 liters per second. Then we need to look at pipeline BC and determine it. So we're going to follow the same procedure. Again, per 1,000 meters, we want the head loss per 1,000 meters. What's the okay, let me just delete all these extra lines that I have here to make it clearer so you can follow it. If we look at it, we had a head here of let me just delete more stuff from here just to clear it all out. It's easier for you to follow. Okay, it's the so now we proceed in the same fashion as we did for AB. 42.2 meters. That's the hydraulic head at point C, and 29.5 is the hydraulic head at point B. So if we subtract 29.5 from 42.2, that will give you the head loss that's occurring in pipeline BC. And that's what's being done here in the numerator of this equation. And then again, dividing it by 0.9, it's for the same reason, to convert it to 1,000 meters. Right, the length over there was 900 meters. So if you want to, you can do whatever answer you get in the numerator, divide it by 900 and then multiply it by 1,000, and it's the same thing as dividing it by 0.9, and it means you get per 1,000 meters a head loss of 14.1. So same procedure again. Go to the nomograph, plot that value of 14.1. The pipe diameter this time is 250 millimeter. So you now plot 250 millimeter, and then you'll then be able to read off the value of Q. And if you do that, you'll come up with an answer of around 73 liters per second. So the total flow, the total flow of water that's arriving at point B would be the sum of that 73 plus the, so it'll be 133 plus that 73. If you add those two values up, you end up with a value of 206 liters per second. So that's the total Q that's available. This as a sideline, you could have worked out also from the nomograph what's the velocity in each of those pipelines, and I'll leave that as an exercise for you. Right, so this is just a brief revision at this point, just to give you an idea of how to use these equations. And in the next lecture, we'll start looking at it in more detail. In the next lecture, I will also look at, in this particular example, with this saying we're supplying 206 liters per second to point B, but in practice, what normally happens, for example, if you're supplying water from a reservoir to a particular township and you're designing the main supply pipeline, then you would first need to determine how much of water you would need to supply. Right? So we would normally start off with this value of Q. And we actually work in the reverse fashion. So we start off with the value of Q. We would then choose a particular pipe diameter. We guess a particular pipe diameter. We do have the information about the ground levels for the particular area where we're installing that pipeline, and we would then need to check whether that particular pipe is suitable or not. Right. So we're going to start off with the amount of water that we want to arrive at a particular point. Right. We know how much we need there, and then we would see, okay, we're starting off the supply from a particular point, and we would install a particular pipe size, and then we see, okay, does that amount of water actually arrive at that point, and what is the head loss in that pipeline? And if the head loss is too high, then we would then increase the pipe diameter. But you'll see that procedure in next week's lectures. So in next week's lectures, there'll be two aspects to it. The one is to select a suitable pipe diameter. In this particular example, you were given the 250 and 300 millimeter diameter. So, but in practice, in actual design, you got to choose a suitable pipe diameter size. So that's one aspect of it. And the second aspect of it is to determine how much of water you need to supply to that load center. So that's what we will also look at those issues in the next lecture. How much of water you need to supply to that load center, you'll see on the Moodle website. I have under water reticulation, the CSIR guidelines are there, and that's what we will use. The CSIR guidelines, they would provide us with guidelines of how much water we actually need to supply to point B in this particular example. Okay, so having said that, I'll end the lecture at this point. I know there's still many students who are not part of the Teams group. I don't know why that is like that. I'll look into that, and hopefully by the next lecture, they would all be in the Teams group and they can join the lecture. Any queries before I end the lecture? Do you have any queries, anybody?
Yes, sir. I've got a question.
Yeah, go ahead.
The 9.79 that we divided the 550 by, how did we obtain that?
Uh, wait, okay, did you attend the first lecture? Have you missed the first lecture, if I may ask?
No, I was there. I did attend.
Okay, okay. Then the 9.79, if you read this section 4.1 of the notes over here, if you read this section 4.1, that's where you would it would come up from there, and you'll see the value there, the 9.79. Now, what does it actually represent? If you look at this diagram, for example, in figure 4.1, if you had, for example, if you took a cube of water, I know you cannot get a cube of water to stand on the ground. You need a container or something like that. But let's take an imaginary cube of water that we have. So it's 1 meter by 1 meter in area of the ground, the contact area of the ground, and it would be 1 meter height like that. What pressure would that 1 meter of water exert on the ground? Right. What does it? What pressure does it actually exert? That's what it is. If you work it out, you'll get an answer of 9.7. Okay. Firstly, what is the weight of that water? That 1 meter by 1 meter by 1 meter. Right. You'll get an answer of 9.79 kilonewtons. Right. And what pressure it would then exert on the ground? It would be simply pressure is equal to force over area. The contact area at the bottom is 1 meter. One times 1, that is 1. So 9.79 divided by 1. So you then get a pressure of 9.79 kPa. So 1 meter of water, right, 1 meter by 1 meter by 1 meter high. Right. So any column of water that's 1 meter high would exert a pressure of 9.79 kPa. So now we have a conversion factor between the two. So if I want to convert from kPa to in terms of so many meters of water, so, how many meters high, a column of water, so many meters high, that's the conversion factor that 1 meter high of water exerts a pressure of 9.79 kPa. So that's why we're dividing it every time by the 9.79. We want to work, we prefer to work in meters of head rather than kPa when it comes to water reticulation design. It's just the way civil engineers work, because we have this, we got to work with the datum, and that normally you'll get from a surveyor, and that would be in terms of meters. So that's what it is. Does that answer your question?
Yes, thank you very much,
Like,
sir.
just to elaborate, so for example, in figure 4.1, if you took now the second, it's drawn there, the second cubic meter of water. So if you now on top of that 1 cubic meter of water, you stacked up another cubic meter of water, then the pressure on the ground would now be 2 times 9.79. If you stacked up a third cubic meter of water, it would then be 3.79. And if you can write it out, you can do the calculations yourself, and you'll see it's actually not no, it doesn't have to be a 1 meter by 1 meter. The areas will cancel off. Right. So even if it's no matter how small, even if it's a 1 millimeter diameter, or 1 millimeter by 1 millimeter, the base area of it of the water is right, and it's just the height. It's a function of the height. It's not a function of the contact area with the ground for that pressure. But hopefully that clarifies that for you. Uh, any other queries? Anybody else? Is there any further queries with regard to it? Anything you haven't understood in this section? Okay, if it's no further queries, I'll stop the recording at this point and then end the lecture. So, okay, the recording has been